So now my calculation is done. So we can go to the output file and we can have a look at my output. So this is my output file. So this is a quadrant system with +1 charge. Actually, its convergence took a lot of time. And now let us see the expectation value of S-square operator. It's 4.61, whereas for quadrant it should have been 3.75. So it shows a large deviation from what should be the ideal value of the S-square operator. The question is that why it shows so much of an value. So this is my HOMO orbital energy, this is my LUMO, and this is the orbital energies of the beta orbitals. So remember, it has 3 unpaired electrons, and all of them in the unpaired in the alpha orbital. And so basically what will be my alpha minus, so HOMO minus 3, that will have degeneracy with the beta HOMO. So this is my alpha minus 1, 2, 3. This should be close in energy with my beta LUMO somewhere here. Now to understand why the spin contamination is so large, we need to look at the orbital pictures. So how the spatial part of the orbitals actually looks like. So in this case we have not given the large print option, so we have to rerun it again. So what we should do is that we should open the input file, with notepad, and give the large print option here. This time it will take much less time, because what it will happen is that after I make my run, you can see that there is already a GBW file created. Here is the GBW file. So it already has the guess for the orbitals, and next time when it will run, it will read from the guess. So it should actually take very small amount of time. You see. So if I now open the FEO again, FEO dot out, is the initial guess orbitals. If I come down a little bit more, it's basically 2 iterations and it is converged, because it has read from the previous guess. Now, because now the orbitals are there, we can actually open them. Because the orbitals are there, we can actually open them in ChemCraft and actually see how the orbitals actually looks like. Before going to that, let us once see the orbital picture. So if I want to see the orbital pictures of FEO, and if I see the canonical orbital, so the way it should happen is that there are 3 unpaired electrons. So this will be on the alpha orbital, alpha HOMO, HOMO minus 1, HOMO minus 2, and the 2 electrons which will be paired is alpha HOMO minus 3 and beta LUMO. So alpha HOMO minus 3 and beta LUMO should be have of similar quality, whereas alpha HOMO minus 3 and beta HOMO should be of similar quality. You expect them to look similar. At the same time, the beta LUMO looks similar to the alpha HOMO minus 2. Beta LUMO plus 1 looks like alpha HOMO minus 1, and alpha HOMO actually looks like beta LUMO plus 2. So these are the orbitals which are relevant for my visualization. So what I will do here is that I will go to the FEO.output file, I will open it with ChemCraft. So now if I go to the tools, I go to the orbitals. So what I would need is the alpha HOMO HOMO minus 1, HOMO minus 2 and HOMO minus 3, and in the case of beta orbitals we need the beta, no, not this one, the beta HOMO, beta LUMO, LUMO plus 1 and LUMO plus 2. Total 4 orbitals we need from the beta and 4 orbital is from alpha. Now we have rendered. Now let us see the alpha orbital. Let me see the both surfaces, and if you go back to the presentation, this is how the alpha HOMO looks like. Let me make it a little here so that you can have a easier look. This is how alpha HOMO minus 1 looks like, alpha HOMO minus 2, this is alpha HOMO minus 2, and this is alpha HOMO minus 3. And about the beta, this is what the beta HOMO looks like. This is beta LUMO, LUMO plus 1. This I have to zoom a little bit more, or I can make this one as normal. I have to rotate it maybe a little bit more. This is how the beta LUMO plus 1 will look like, and this is what the beta LUMO plus 2 will look like. Now see the difference. If I go back to my PowerPoint presentation, the spatial part of alpha HOMO minus 3 and the beta HOMO should have been same, because they are actually correspond to two of the paired electrons. These three are unpaired, but these two are supposed to be paired. So if I think of normal molecular orbital theory, whatever is my HOMO minus 3 alpha and my beta LUMO, they are supposed to look same, but actually if you do an UHF calculation, they will look different. Now this different in the spatial part is what it leads to spin contamination, because the alpha and beta, even the two electrons are in a similar orbital, their spatial part are not same. So that means their spin part will not cancel out, it will lead to spin polarization. So this will lead to a severe spin contamination problem, and not only it will lead to the spin contamination problem in terms of visualization, also in terms of making chemical sense out of it also, this will make it more complicated. So in the terms of visualization, what one should definitely do is that to visualize this kind of orbitals, one need to go to what is called a quasi restricted orbitals or QROs. Why you need to go to QROs? Remember, in the case of unrestricted orbitals, they were generated from the solution of two different Fock matrices, Fock alpha and Fock beta, and that is why if you and they are diagonalized separately, so they are not orthogonal to each other. And what is done in the quasi restricted orbital is that you orthogonalize this orbital after you generated them, and that leads to a new set of orbitals which are actually orthogonal to each other, and they are basically more easy to interpret. If I now want to look at it, let us do one thing. For the same input file, I have to run it. To generate the quasi restricted orbital, I have to use the keywords UNO. So this will generate the unrestricted natural orbitals as well as the quasi restricted orbital. Let me save it. And once it is generated, you see this one is a QRO. Now to visualize the QROs, there are two options of doing that. One is that I can use the Orca plot utility to generate the cube files, or I can read this QRO, put them to a guess to a new calculation, and basically don't do the Hartree-Fock iteration. So it keeps the QROs as it is, and then I can use ChemCraft to actually do the printing. So to use this alternative, what I need to do is I have to go to this feo.no. I will save it as a new input file. I will call it a qro.inp. So to read the guess from a different file, by default Orca reads a guess from a GPW file which actually has the same name as your input file, and if it cannot get the GPW file, then it will generate the guess, otherwise it will read from that file. What I can do, I can use the MORead option, and then I can give the name of the input file within the quotation. You have to give the name of the file, and in this case it is feo.qro. Remember, the MOINP input start with the percentage, and you have to be careful with the capitalization, and this is called FEO. So F is capital, E is small, and then the O is capital. Need to be careful about the name. And now if I save it, and I have saved it as the name feo.qro. Okay, I missed one keyword, that is no iter, because if I reiterate, then my Hartree-Fock will override the orbitals which were treated as guess. So I have to use the keyword no iter, so that it will not do any iteration, it will just read the QRO and then print them. Now let us see the output file. So it has read from this feo.qro. It says that the ROHF occupation numbers were taken from no iter, MO orbitals were renormalized, reorthogonalized, and because there was no iter keyword given, you will see that there is no Hartree-Fock iteration has been done, and it says that the orbital in population did not come from a converged calculation because we do not wanted it. And now after it is done, so you can see the orbitals now. It is your alpha homo -1, homo -2, homo -3. and this is your beta. Now see the orbital energy of the beta HOMO. It's 15.623, and what is alpha HOMO minus 3 is 16.6233. So they are now almost have become similar, and because of this one they will be more easy to visualize, because you can get an idea about the energy level of these orbitals. Now let us try to open them in the ChemCraft. I can open another window so that you get an idea how they looks like. It's FeoQRO.out. I have to open it with ChemCraft. I go to the orbitals, and again the same way I have to do alpha orbital HOMO minus 1, HOMO minus 2, HOMO minus 3, and I also need to see the beta orbital. It's beta HOMO, LUMO, LUMO plus 1, LUMO plus 2. Now see the alpha orbital 15, that is HOMO minus 3, and that should be same as my beta HOMO. See, they are same. Similarly, my alpha minus 2, this is how this looks like, that should be same as my beta LUMO. My alpha HOMO minus 1, this should be same as my beta LUMO plus 1, and alpha should be same as my beta LUMO plus 2. And if you see the picture, that's what you will see. So it will be a good idea if you can go and visualize each orbitals individually, and this tells you why in the case of UHF your spin contamination is so high, because the spatial part of the alpha and beta orbitals are really different. So they will not cancel out each other, and that will lead to a residual spin polarization. And that is why these orbitals are very difficult to make chemical sense out of it. If you really want to make chemical sense out of it, it's a good idea is to use the QRO utility. So use the keyword UNO, generate the QROs, read them without doing any iteration, and then you can visualize them, and then you can make chemical interpretation out of it. Next thing what we are going to do is to get to the idea of spin density plot. So we are going to take this a little kind of systems where you start with an ethylene and replace the terminal group by a CH2 or a sulfur or beryllium, and we are going to see how the spin densities looks like in each case. So I will start with one example, the first one, and then we will see how to do that. So to do the spin density thing, what we need to do is to first let me go to Avogadro to make the structure. So it's carbon, it's a double bond, and now I am going to make a single bond out of it. Or I could have directly make a double bond. Maybe I should not use the adjust hydrogen utility. Let me remove this hydrogen first, go back there, and now I can add the hydrogens. I add one, oh, and I add the other. Once I did that, I go to extension, optimize the geometry. So this is how the molecule should look like. So let's see how many carbon it has. It has 3 carbons, 1, 2, 3, and how many hydrogens it has. So total the number of electrons should be 18 from the carbon and 1, 2, 3, 4, 5. So total 23 electrons, so it will be a doublet. So if I now make the input file, let's say I go to Orca, I generate the Orca input file. This cannot be, I think this will be doublet. And this I should now generate the input file. What is the name? I should keep it. The first one. Let's say call allyl.input. So my calculation is done. This is my calculation. It's little bit spin contaminated. Now let us see the spin population. If I go by this nomenclature, this is my terminal carbon, this is my central carbon, and this is the carbon of my substituent group. So if I add these three substituent, the resultant value will be 0.99. So I need to add all of them. Maybe I need to use a calculator utility. Should have been minus 0.069106 minus 0.074671. So it is 0.85. My central C is minus 0.74. And my terminal C is 0.99. We can also visualize how the spin density plot actually looks like. To do that, we need to use the utility Orca plot. y.gbw minus I. So that first I need to select the type of plot. I want spin density. So it's 3. Enter the number of orbitals to plot. This is only spin density. The plot type is already a cube. So the only thing I need to do is to generate the plot. And if I now go to the file, there must be a cube file. What does it say? It's allele.spindensity.cube. So let's find out. City file, somehow the cube file has not generated. Maybe we have to give the format of the file. Select of the output file, format 5, and that's, I have to give Gaussian cube. And let's try it again. allele.spindensity.cube. Here is the spin density.cube file. So I open it with Chemcraft. Let me close this one. I have to reduce the contour value a little bit. And if you see the contour value, and from the scale you can see from the color, so these two carbons are actually now positively charged, you see from the color, whereas the central carbon is negatively charged in terms of spin density. Charge is not a correct statement, it is a sign of the spin density. So this have the positive spin density, this the terminal carbon and the substituent one, whereas the middle carbon, the central carbon, has the negative spin density. So you can visualize the spin densities like that, and you can actually make chemical sense out of it. Now the one thing what we are still left with is the open shell calculations in the low spin state. And let us take the example of lithium. And lithium, you can have two kind of closed cell systems. In the, of course, the first kind of closed shell system is where all the electrons are paired up. In the case of lithium, you can have basically two kind of singlet state. In the first kind of singlet state, all the electrons are paired up. So this will looks like this. Of course, you can have the triplet. This will have MS value 0. You can have the triplet state where both the electrons are unpaired. On the other hand, you can have a state where one electron is at lower orbital and the other electron is as another orbital, and this can actually get paired up. So I am talking of lithium dimer. So where its configuration is 1:2:1, and if I have two of them, what it can do is that, so one of the two electrons can get some kind of a coupling, but this can be of any possibility. This can be of this possibility or this possibility. Both of them are equally probable, and their linear combination actually leads rise to the formation of a open shell singlet state. And how you calculate this open shell singlet state is that you use the flip spin option. So in this case, you start with the triplet state and you flip the spin, and the spin vectors actually says at what center you have to flip the spin. In this case, I have written flip spin is equal to 1. So that means it will do the flipping of the spin at the second center, second lithium in this case. Similarly, if there are more than two atoms, you can give it like an array, and counting start from 0. And what is my final MS value? That's also important. In this case, I want singlet. So I need to give this final MS value as 0, and I have to start with the triplet state. So I can do this calculation and I can tabulate all the possible options here, and we can find out which state is actually lowest energy state. So, this also I give as an homework problem. So, I believe with these lectures about open shell systems, you have able to understand how open shell are different from closed shell systems and how one should treat them. I hope by realize you have understood the spin contamination can be a problem in cases. So, at least if you cannot fix it, you should be able to aware how much is the spin contamination. So, if you are doing a calculation on the open shell system, you should actually look first at the spin contamination value, charge, multiplicity, orbitals to make chemical sense out of this kind of systems. So, what we will do now is that in the next few classes we will see how to do correlation treatment on open shell systems and how the spin contamination actually affects the correlation treatment. Thank you.